not be here in person because of visa issues, and then the second speaker, who is going to at least do a live Q&A, won't be here because of flight delays. So we're going to have a recorded video for the first talk. So it'll be easy, but I do highly recommend reaching out to Julio if he's here later today, once his flight gets back, or directly contact Tianwei if you have any other questions for the talk. But with that, we have our first talk today, which is Time Lock Puzzles from Lattices by Shweta Agarwal, Julio Malavolta, and Tianwei Zhang. So we'll watch the video for this.
The first part is an introduction to the topic, Hemlock puzzles. The second part is Hemlock puzzles from
Okay, as soon as the sound issues get worked out, it'll start.
Hemlock puzzles. The second part is Hemlock puzzles from sublinear randomized encoding for. Hi everyone, I'm Tianwei Zhang from Max Planck Institute for Security and Privacy and Huo University Bochum. This is a work about Hemlock puzzles from Lattices, and it's with co-authors Shweta and Julio. This talk consists of 5 parts. The first part is an introduction to the topic, Hemlock puzzles. The second part is Hemlock puzzles from sublinear randomized encoding for repeated circuits. And the third part is about another variant of Hemlock puzzle called Hemlock puzzle with setup. Then a detailed analysis of sublinear randomized encoding for repeated circuits, which is also the technical core of our paper, and finally, the conclusion. The hero of this talk is going to be something called Hemlock puzzles. So let's begin with what they are. Time log puzzles are a cryptographic primitive where a message M is locked for a certain amount of time, which means that it should take a lot of time to open this message. It has two key features. One is fast puzzle generation, which means that the time taken to generate this puzzle should be fast, ideally logarithmic in t, and sublinear in t at most. Another feature is that although generating this puzzle should be fast, solving it should take a lot of time. Even if you had a very powerful supercomputer, which can do a lot of parallel computation, you should not be able to do it much faster than with time t. The mathematical way to model this is that the circuit that opens this puzzle has to have a depth at least t. Well, what are the applications of such a primitive? Basically, you can encrypt to the future. You can always talk to people in the future if somebody is prepared to spend the computation time to open it up. But more concretely, you can do sealed bid auctions, non-malleable commitments, and minor extractable value prevention. What's more, time lock puzzle has many other applications in the field of blockchain and cryptocurrency, such as blockchain front-running prevention, fair contract signing, and cryptocurrency payments, and so on. In this work, we propose the first constructions of time lock puzzles based on lattices. More in details, we obtain the following two main results. In the pre-processing model, we allow for a one-time public coin setup, whose runtime can depend on t. In this model, we obtain a time lock puzzle, where the puzzle generation time is logarithmic in t, and the puzzle solving time is linear in t. In the plain model, where there is no pre-processing, and the encryptor does all the computation, we obtain a time lock puzzle, where the puzzle generation time and the puzzle size are both bounded by square root of t. To obtain a time lock puzzle, we also construct second randomized encoding for repeated circuit computations, which we believe is of independent interest. As an example, we show that our sublinear randomized encoding for repeated circuits yields the first non-interactive coupled RAM scheme with sublinear encoding complexity in the number of steps t without using I/O. We also introduced the notion of range punctual PRF for the construction of sublinear randomized encoding for repeated circuits. Range punctual PRF is a pseudo-random function where we can puncture keys to remove from the evaluation domain an entire range of points. Although technically, this is allowed by the standard punctual PRF syntax. The issue is that the size of the puncture keys will grow with the number of puncture points. For our application, it's crucial that the size of the puncture key remains constant. Therefore, we need to introduce this new notion. Before talking about the construction of time lock puzzle from sublinear randomized encoding for repeated circuits, let's recall that an SRE for repeated circuits takes as input a circuit C, an input X, a repetition parameter T, and returns an encoded tuple C T tilde X tilde. The encoding algorithm takes time sublinear in T. Anyone can then evaluate the encoded tuple C T tilde X tilde to obtain the T-fold evaluation CTX. The evaluation algorithm takes time T. The security of such a primitive guarantees that no further information other than CTX is revealed about X. For a T-folded sequential function f, we can define the following TLP circuit CF. Unless I equals t plus 1, it simply computes fx and increases the index I to I plus 1. If I equals t t plus 1 and b equals 0, it returns m. If I equals t plus 1 and b equals 1, it outputs x, or z instead. We denote CFT, the t-fold repetition of the TLP circuit CF. We then simply define our time log parcel to be an sublinear randomized encoding for the t-fold repetition of the TLP circuit CF on input 0, x, m, 0, 1, where x and m are uniformly randomly sampled. We then sample R uniformly randomly and use the Goderich-Levis inner product R.M to mask the secret S. To solve the puzzle, we compute the sublinear randomized encoding evaluation of the encoded tuple and dot it with R to unmask the secret S. It's easy to verify that the above scheme is correct, since the t-fold repetition of CF on input 0, x, m, 0, 1 equals m by the definition of the TLP circuit CF. Here's a sketch of the security proofs where the second equality holds because m is uniformly randomly sampled, and for the other steps, the circuit is functionally equivalent, and thus indistinguishability follows directly from the security of the sublinear randomized encoding for repeated circuits. We also know that in the last hybrid, the puzzle is effectively just the encoding of FTX XOR M. Now we can argue that any adversary that's able to output M in time less than t will also be able to compute FTX, the t-fold evaluation of F on input X, therefore violating the sequentiality of F. In the above reduction, we have applied the depth-preserving Goderich-Levis theorem to show that being able to compute R.M for a pseudo-randomly sampled R implies that knowing M. Now let's move on to talk about a variant of time log puzzle. Time log puzzle with setup by combining reusable Gabor circuit and laconic function evaluation. We first construct a depth-independent reusable Gabor circuit, where the output pk of the Gabor algorithm is independent of the size of the output size of C. Security of reusable Gabor circuit guarantees that it's possible to simulate the Gabor input x tutor with the output Cx. For efficiency, the Gabor and the evaluation algorithm take time poly lambda times the size of C, and the encoding algorithm takes time poly lambda times the product of the input size and the output size. The construction of time log puzzle with setup is very similar to the previous one, since we just replace sublinear randomized encoding for repeated circuits with depth-independent reusable Gabor circuit. In this one-time setup, we compute CFT tutor and PK by using reusable Gabor circuit to Gabor the circuit CFT. Note that, as its name implies, reusable Gabor circuit is of course reusable, since after this one-time setup, we can generate polynomially many different puzzles in time just log t. Now, finally, it's time to take a look at the technical core of this work, the construction of sublinear randomized encoding for repeated circuits. The first observation is that since the preprocessing, the gabbling is reusable, we can hope to amortize the work. We can try to chop the execution of ft in square root of t many blocks, each of size square root of t, to reduce the complexity of the encoding. We define the following circuit, capital F square root of t. It takes input x and I. If I equals t plus 1, it outputs x directly. Otherwise, if I is less than t plus 1, it computes y equals f square root of tx and outputs an encoding of yi plus square root of t. The idea is that for encoding, we can run the preprocessing, the reusable governing algorithm once for the circuit, capital F square root of t, and then compute a encoding of x1. For decoding, the first evaluation would return a valid encoding of f square root of tx square root of t plus 1, which we can feed again into the evaluation algorithm to compute an encoding of f2 square root of tx 2 square root of t plus 1, and so on. And so on, all the way until we compute ftx at the end. However, the above attempt has a huge problem. The size of such an encoding depends on the output size of the circuit, which means that it grows exponentially with the number of repetitions. To fix this problem, we use split fully homomorphic encryption scheme. When doing the homomorphic evaluation, one can compute a small hint HJM, whose size is independent of the size of JM. This small hint would allow us to decrypt the evaluated ciphertext. Our idea basically is to alternate the computation of sublinear randomized encoding for repeated circuits with the computation of the split FETE. In other words, we modify the circuit capital F square root of t so that instead of computing the output directly, it outputs the hint of the FHE computation of the circuit gamma I pk bar. The circuit gamma I pk bar takes input x and the range punctured PRFK ki plus 1. We denote ki plus 1, the PRFK punctured out the closed interval 0 to I. The circuit first computes y equals f square root of tx and returns FHE ciphertext ci plus 1 of y ki plus 2, which is a range punctured PRFK punctured out the interval 0 to I plus 1, and an RGC encoding EI plus 1 of YI plus 1 PK bar CI plus 1. Concretely, the sublinear randomized encoding now consists of the reusable governing of the circuit capital F square root of t, a FHE ciphertext C1 of x, and a reusable gobbled circuit encoding E1 of PK1 x1 PK C1. To decode for I from 1 to square root of t, we first homomorphically compute the circuit gamma I pk on input ci, and then decode the hint hi from the reusable gobbled circuit encoding ei, and finally get the next tuple ci plus 1 ei plus 1 by decrypting the hint and the ciphertext c. At the end, we output the reusable gobbled circuit evaluation of capital F square root of t tutor on e square root of t plus 1. This way, the evaluator can use the information output by the sublinear randomized encoding to compute the new encoded input. Since the size of the hint hi is certain, which is independent of the output size of the circuit, this allows us to avoid the circular dependency in the parameters of the above attempt. Finally, we conclude this talk by summarizing this work and talking about some open problems. We have constructed two time log puzzles One is time log parcel with setup, where the setup time is t and the parcel generation time is log t. The other one is time log parcel in the plain model, where the parcel generation time is square root of t. We introduced the notion of range punctuable PRF and sublinear randomized encoding for repeated circuits along the way. In the appendix, we also construct a heuristic fully efficient sublinear randomized encoding for repeated circuits. Hence, a time log parcel in the plain model with log t parcel generation time. Here are some open problems. The first one is how to construct lattice-based fully efficient sublinear randomized encoding for repeated circuits so as to get a time log parcel with log t parcel generation time in the plain mode without any preprocessing. The second one is that how to construct lattice-based time log parcels with some desired additional properties, such as homomorphic time log parcels or batch solving time log parcels. Thank you for your attention. If there is any other question, please interact with Julio in the following Q&A session. Thank you. Bye-bye.
All right, and again, Julio might be around later today. If you catch him, have any questions, feel free to talk and reach out to him. With that, we're gonna move on to the next talk in this session, which is cryptanalysis of lattice-based sequentiality assumptions and proofs of sequential work. And Yitong will be giving the talk.
Okay. Yeah, thanks for the introduction. And I'm Yi. This is a joint work with Cody Freitag, and we are going to present an attack against a lattice-based system and its proof of sequential work system. So maybe firstly, what is a proof of sequential work system? And same as the time lock puzzle we've seen in the previous talk, it belongs to the so-called timed crypto, the category of timed crypto. It is proposed by Samir and Wagner in '96. And in time crypto, roughly speaking, we have a main crypto operation that would take a physical time maybe of t. And in the POSW, in particular, we would have a prover and a verifier. The prover would run an inherently sequential process, and prover has parallel computational power. So this process is measured by its parallel depth t. And the prover then would try to convince the verifier of this sequential work. And here we would desire a weak verifier, and the verifier don't have parallel computational power, and is measured by its just standard running time. And for this verifier to be weak, we would maybe want a log t running time. And for the soundness of this kind of protocol, we would like that convincing the verifier should require the parallel depth of the prover to be roughly t. And since we have this parallel depth as the measure in the soundness, it does not help too much by having more parallel computation power. So one application of this kind of POSW system is maybe in the blockchains, maybe in Bitcoins. If we replace the proof of work by POSW, then a huge mining farm would not help, and it might help with the energy conservation in those kind of blockchains. And when it comes to the post-quantum security of the POSW systems, most prior constructions are based on the number theoretical assumptions, for example, from factorings, and they are broken by quantum computers. However, last year here, Lai and Malvolta proposed a lattice-based POSW candidate. While in this work, we managed to break this POSW construction from lattices and also break its assumptions as well. And in a bit more detail, the LM23 scheme considers a sequential SIS problem with certain parameters. And assuming this certain problem requires taps roughly t to solve, it's the LM23 scheme then is a construction that would require the preferred depth of also roughly t. And our first attack breaks the sequentiality assumption in this 2023 work. And we show that this particular problem can be solved in only depth log t. So this is way less than the linear t time, depth they assumed. And moreover, we can allow a depth norm trade-off and break a wide range of parameters for this sequential SIS problem. I guess in usual cases, when people break an assumption underlying some construction, they could maybe quickly modify their attack and extend to the construction as well. But however, in our case, we tried a bit harder and then have another strengthened attack against their POSW scheme. So it turns out the scheme is broken in depth log squared t, which is also polylog and way less than the linear t time, t depth. But with a caveat that we can only attack a slight variant of their construction. The difference here is only some arbitrary design choice, and it even does not touch this soundness proof in their work. We'll see this difference later on. And maybe to see more details, firstly, let's see what's the sequential work considered in the LM23 construction. And on a high level is to iterate the SIS hash function t times. And this SIS function is mapping from length m bit strings to length n ZQ vector. And to iterate this hash function, we really need a backward map that maps back from ZQ vector to bit string. And here we pick the bit expansion function G inverse that is taking in the ZQ vector and replace every ZQ entry by its log q bit representation. So it's expanding the length n vector to length m equals n times log q bit string. And this notation G inverse is due to the existence of this kind of gadget matrix G. It satisfies that if we multiply G on the left, we could recover the expanded ZQ vector. And we would use this canceling property frequently later on. So to put it all together, the sequential work would start with some given A matrix and U0 initial vector and iterate, and finally output the UT results. And it's depicted as on the right. We have U0 and we pass through the G inverse to get X1, and we time minus A on the left to get U1 and repeat. And just to note here, we use minus A instead of just A, just for some convenience later on. So for this sequential work, it can actually be expressed by in some linear form with this huge A matrix. And we can quickly verify how this really encodes the sequential work. For the first row, we have G x1 equals U0. This would correspond to the fact that x1 is defined to be G inverse of U0. For the second row, it's AX1 plus GS2 equals 0. And this is because AX1 would be minus U1, and GX2 is again U1. So they cancel to 0. And the same canceling happens to the following rows. And we have a lot, maybe the last row is a special case. We have just AXT equals minus UT. This is also by definition. And right here, we would denote the system without the last row as the black AT system, and with the last row as the orange AT system. They are, we would let the solver set the value of the last minus UT. So the black and orange system are exactly equivalent, and they are used differently, basically only for some convenience. And with this linear form, the sequential SIS problem is defined in this way, and it has a main parameter, which is the norm bound B. And an instance to this problem is the uniformly sampled matrix A and the initial vector U0. And the goal in this system, problem is to find the solution X to the black system in particular, where every entry of X is bounded by the norm bound parameter B. So with this sequential work, the LM23 construction aims at proving the knowledge of a short solution X to, let's say, the orange system, and prove this to a weak verified. In the LM23 construction, they take a standard divide and fold approach. Here, for simplicity, let's say T, the time the depth parameter t is in the odd case where t is 2 t prime plus 1. And in this odd case, we can split x into the top half, the bottom half, and the remaining middle entry, maybe the middle part. And correspondingly, the linear system also splits in this way. So for the big A matrix, we can split A T prime matrix on the two corners. And in the middle, we are remained with the G stack, some G stack A middle part. If we carry out the multiplication, they would also like multiply into 3 terms. It can be quickly verified. In the middle, we indeed we can cancel the plus minus U entries, and they cancel to 0. So the right-hand side is indeed sum to U0 on the top and zeros in the middle and minus UT at the end. And the idea in the LM23 protocol is that if the prover review the middle entry to the verifier, then the linear system would be left with only the 2 blue top and bottom halves. And since they share the same AT prime matrix, we can take a random linear combination of them, and they are folded into a reduced system with only scale T prime, which is half of T, and the protocol could just recurse and continue. Right, and exactly in this protocol, the prover would review xt plus 1, and the verifier checks this is a short reviewed information. And verifier send a random challenge C, which is also short and roughly bounded by n, to the prover. The prover and verifier then fold by taking this random linear combination using the random challenge C. And they could, and here after the folding, right, we can see this if we represent the folded value by some x prime vector and u prime vector, they would have exactly the same form as the equation we were beginning with. So the prover and verifier could just recurse to prove the folded system. And here another note is that this is the place where we differ from the original LM23 protocol. So in their original protocol, they have the C, the multiplier C, the channel C multiplied on the bottom second half instead of the first half we write here. And to remark again, this is as we can see here, this is really seems to be a arbitrary design choice, and in particular, it does not affect the soundness proof of their system. So regarding the norm bounds in this protocol, in each round, when we fold x into this x prime, the norm of x would grow by roughly the size of C, which is also roughly n. So after we have log t rounds, the final norm bound used in the protocol would be n to the log t. And in their soundness proof, the reduction also loses a similar factor. So the final reduction is from the sequential SIs problem with the norm bound, with the norm bound of n to the 2 times log t. And our attack would crucially exploit the gap between this n to the 2 log t bound versus the honest binary bound. So let's then get into our attack. On a high level, our attack would construct a Michel-Piker 12 style trapdoor R for A, satisfying that if we multiply R on the right, we could get a G stack 0 structure. And we are going to construct only a somewhat short trapdoor R for A. Then this would be exploiting the fact that there's a, right, as we just see, there's a gap between the norm bound in their soundness property versus the real honest binary norm bound. And more importantly, we construct R in a recursive manner, and so that a recursive divide and conquer manner, so that the computation for R only takes low computational depth. Suppose we get this kind of trapdoor R, we can then take the solution X to be R times R times the G inverse of the initial U0 vector. And it can be verified this indeed satisfies that AT times X equals U0 stack 0. This is mainly because some canceling of G and G inverse. And if we get this kind of somewhat short X, this would directly solve their sequential SIs problem, and for a wide range of parameters, and in particular, including the setting of LM23. And to break the LM23 construction, we need to work a bit harder and design the recursion more carefully, so that the resulting X we get could interact well with the folding. And we would run this honest prover with the solution X we get from the recursion. So how do we recursively construct this kind of a trapdoor? Suppose we start with a block lower triangular matrix L. In this form, it has L0 and L1 on diagonal, and below the diagonal, it has some sparsity structure where only the top n rows is some non-zero, non-empty W matrix. And for example, we would set L to be AT as the entry to this recursion, and it can be verified AT indeed has this kind of lower triangular and sparsity structure. And suppose by recursion that we have already computed the sub trapdoors R0 and R1 for L0 and L1 parts. And an important thing is here we compute the sub trapdoors in parallel. And at the end, we can see that this helps to get the low depths for computing the trapdoor R. With the R0 and R1, we combine them to a trapdoor R for the entire matrix L. And with this form, we have still R0 on the top, but on the bottom, we have R1 times some G inverse matrix. And it can be verified this indeed satisfies the desired property as a trapdoor. The important part here is, again, the way we construct this G inverse multiplier is to just exactly for canceling the effect of this corner W matrix. And just by the way, the base case is L equals G, and the trivial trapdoor is the identity matrix. Right, and with this recursive construction for the trapdoor R, we can see that at each level of the recursion, the only roughly the only change is this G inverse matrix, and the norm of R would grow by a factor of this G inverse matrix. And this is a M by M matrix, and it's a binary because this G inverse is to recall is a bit expansion. So this G inverse matrix this norm is bounded by order M, and the depth for this recursive step is constant because it only involves some matrix multiplication, which is parallelizable. And yeah, as a result, our attack using this recursion could find a solution with norm order M to the log T. This is because we have log T levels of recursions, and the depth of the overall recursion is constant on each level and log T level, so it's still log T depth. And more generally, if we take the branching factor of our recursion to be some general K factor, which means instead of just split L into L0 and L1, we split maybe into K parts, then we can have a norm depth trade-off. And an interesting setting here is when we set K to be a small polynomial of T, we could achieve both polynomial norm bound and small polynomial depth. And then we continue to break the LM23 protocol, but here we might meet with some problems. And first, let's recall some behavior of their construction. If you recall in the protocol, the prover would review some middle entry to the verifier, and the verifier would check this reviewed value is short. So in particular, the first check is exactly for the middle entry, the X half entry, and it's checked whether it's an honest binary shot. And the second check is after the first folding. So it's the middle entry of the first folded vector, and it would be like C times the quarter value plus the 3/4 value, and it's checked against the slightly increased norm bound N, and etc. And the issue here is that our recursion, our recursive construction does not have a good norm profile that is desired by the folding process. On the left, it's depicted the profile needed in the folding, and on the right, that's the resulting profile if we run our recursion. An important observation here is that if we just look at the middle entry and maybe the quarter entries, on the left, they are actually among the shortest entries, but on the right, they turn out to be among the longest entries. So it's not aligning well with the folding. And just to give a high-level idea of our solution to this issue, we carefully divide L into K pieces, but this time very unevenly, and it is a carefully defined scheme. And so as to have the resulting norm file for X matching what is really needed in the folding. And our attack would finally pick K to be log T at each level of recursion and still have log T levels. So this is breaking the LM23 POSW scheme, well, with the change we mentioned in depth log square T. And that's the end of our attack. And for open questions, it still remains open. Is there an attack against exactly the original LM23 POSW scheme? So the original one would have the challenge on the second half, if you recall. Or can we actually prove its soundness from other plausible lattice assumptions? Note that here, if there's a proof, the proof should need to really rely on the position of C because we have an attack if the position changes. And more generally, can we construct lattice-based time crypto differently? Fortunately, we have already seen the talk just before. That's the end. Thanks for your listening, and questions are welcome.
We have time for a quick question if there's one from the audience. Okay, I'll ask one. Can you think of if there's any like high level intuition or anything for why there was an attack on the scheme just to learn for the future, or was it more like a particular fact about the norm bound or something that led to the attack?
Right. I think we do need the norm bound to be at least not just honest binary norm bound, so that we can have some space for this parallelized attack. In fact, our maybe norm depth trade-off, I guess on one extreme, you can have a fully sequential attack that has should have the binary achieve the binary on its norm bound, but that's the fully sequential, and that's not really breaking the sequentiality.
Okay. So
right, I think the norm depth trade-off is some inherent feature of our attack.
Okay. Let's thank our speaker again and get set up for the next talk. So for our last talk of the session, we will have a talk on cryptanalysis of algebraic verifiable delay functions, and Gaetan Laurent will be our speaker.
Hi, is it better like this? Sorry. Should I start again, or is that okay? So verified delay function. So one particular use case is to build a randomness beacon. Every user will contribute some input, then you hash everything together. And as long as one input is random, you know that the output will be random. Unfortunately, in a blockchain context, there's a small problem that the last user contributing would know all the other inputs, and that will give him an edge to try to bias the output. And one way to avoid this is using a VDF, because now it takes a long time to test your input, to test what is the output that corresponds to it. So I will look at a particular type of VDF. There are many different ways to build them. And one particular way is using technique similar to symmetric cryptography. And you basically build a hash function using operations in a large field, additions and multiplication. You use a very large number of rounds so that your function is slow. And then you use a zero knowledge proof on top of it to make it verifiable. And that's a relatively attractive way to build it. And in terms of construction, you will need some nonlinear operation. And what you can use for your S-box is to compute a root in the field, so the eighth root for some small value A. And this is attractive because this function is a permutation if you choose A properly. And it's an operation with relatively high degree, and it takes some time to compute, because the natural way to do it will be to see the root as an exponentiation to the power of the reciprocal of A, and you can compute this with fast exponentiation. So it takes log p squaring, basically, to compute the root. So it's not super slow, but it's still somewhat slow. But in terms of the proof, you don't need to do it with 256 operation. You can just do it the other way. Instead of proving that y is the root of x, you prove that y to the a is equal to x. And this is a low degree equation, so it's efficient to prove. So that's why this is used in different candidates, in particular in Sloth++, in Vido, and in Minroot. More precisely, here is Minroot. That's one particular VDF candidate. So you can see it looks like a symmetric construction, like a type of Feistel scheme, and you have this root operation here to make it nonlinear and to make it into a good hash function. And Minroot has a very concrete security claim. They claim that even if you have 2 to the 128 processors and 2 to the 128 memory, you should get a speed up at most 2 compared to the standard implementation, but we'll just do the steps one by one and use fast exponentiation. So how do we do cryptanalysis of this type of object? Well, from my point of view, this is essentially just a slow hash function. It's an object from symmetric cryptography, and it just has a weird security claim, but it's not a claim of security for a hash function. It's just a claim that there is a high delay to compute it. And the delay is measured as, it's a latency, actually. It's the time between getting the input and producing the output. And we only care about the delay. We don't care about the total number of operations, because we can, if we have an algorithm that is parallelizable with lots of operation, that's fine as long as the delay is small. And there could be two potential ways to try to break those constructions. One would be to find shortcuts in the iteration when you have a large number of rounds. And the other option is to just look at one round and to try to make it faster. And in this work, we're looking at the second option. So we just look at one round function. It looks like this. And the main operation that takes time is the computation of the root. So this is what we focus on. And so the goal is to try to compute this root faster than the fast exponentiation algorithm. And in order to do that, we make one interesting observation, that this operation, the root operation, it has some nice property. In particular, it's a homomorphism. This means that the root of x times y is the root of x times the root of y. Of course, that's a very obvious property, but it's actually very useful in terms of cryptanalysis. In particular, it means that you can randomize your input. If you're given some value x and you want to compute the root of x, you can multiply x by r to the a. And then if you know how to compute the root of this y, you can deduce the root of the original x, because the root of x is just the root of y times the inverse of r. So that's very useful for cryptanalysis. If there are some values that are easier to compute, we can randomize and use those values. And in particular, something interesting is that you can pre-compute r to the a and r minus 1. So those are just constant values, and we don't care about how much it costs to evaluate them. And so I will now show you two ideas that we've been looking at in order to break this the sequentiality of the root computation. The first one is to use pre-computation, and it's actually a relatively obvious trick. we're going to pre-compute roots of small values I. So we pre-compute the eighth root of I for some i's. And then when we get an input, we randomize it, and we check if the randomized value is small enough so that it's already pre-computed. That's very simple. And in fact, if you look at the algorithm, it just looks like this, and it's very similar to the baby step, giant step for discrete log computation. You do some pre-computation, and you repeat until you hit your pre-computation. So if you write it this way, you have a loop. So there are lots of operations. The complexity is about square root of p. So in a normal context, that's completely useless. But it's interesting in a VDF context because you can parallelize it. You can compute the loop in parallel. If you have square root of p processors, you can have small processors like this. Each box is a processor, and each processor just do a few simple operations. Each one will use a fixed value to randomize, which is actually hardwired into the processor. And the processor just have to randomize the input x by multiplying by r to the a. Then it checks if the value y is small, and if it's small, you just do a table lookup to recover the value that was pre-computed, and you multiply by the inverse of r. So the latency is just 2 multiplication on 1 lookup, so that's very fast. But of course, you need some number of processors. And if you look at concrete parameters, in the case of mean root, for instance, the prime p is about 256 bits. So you need about 2 to the 128 processors and 2 to the 128 memory. And that's essentially the security claim of mean root. So we're not breaking it, but we're getting very close. The second idea we considered is based on smoothness. So we are, again, we're going to randomize the input that we get. And now, instead of checking if the value y is in a set that we pre-compute, we're going to check if y is smooth when we see it as an integer. I mean, y is a modular value normally, but we can also see it as an integer. And if we are lucky, we can factorize it into a product of small factors. And therefore, if we start by pre-computing the roots of all small factors, sometimes the value y will be smooth, and then we can directly deduce the square root of the root of y, which is the product of the root of the small factors. And this algorithm is actually very similar to index calculus for discrete logarithm. So we know the complexity of this type of algorithm. It has a sub-exponential complexity. So again, if you just want to compute a root, that's not an interesting algorithm. It has a lot more operation than just doing fast exponentiation. But in a VDF context, you can parallelize it, and it becomes interesting. So when you parallelize, you will have a group of processors. So the green boxes are groups of processors. In each group, you start by randomizing your inputs, and then you will have many small processors that just do trial division by one fixed small primes. And then you just have to combine the result of each processor that will answer whether it's divisible or not. And you just gather all the results, you multiply them, and you deduce the root that you're looking for. So the latency is 1 multiplication, 1 trial division, and some multiplication at the end to combine. So it's, again, a very low latency algorithm. And if you look at concrete parameters for a 256-bit prime, there's a trade-off between what bound you use for the smoothness and how many processors you will have. And one interesting trade-off point is using around 2 to the 55 processors. And in terms of latency, you get a speed up roughly 42 compared to the fast exponentiation algorithm. So now this is very clearly a break of the security claim of mean roots. And something a little bit surprising is that actually this is not a new result. This was already in the literature. There's a paper from Stock 1988, so that's quite ancient, where they use exactly this idea to compute modular exponentiation in parallel. So that's exactly the same trick. But somehow this was apparently not really known by people who designed VDF functions, but this is something that was in the literature. And so in the remainder of this talk, I will try to improve this technique and to reduce the number of processors needed in order to make it even more of a break. So one trick that we can use to improve this is to use, instead of asking y to be smooth, we can have y that is what we call almost smooth, meaning we want it to factor into a product of small primes and one medium-sized prime. And this is something that happens with some probability. And if it happens we can also directly compute the root of y from the roots of the small primes and the root of the medium prime. So we have to pre-compute also the roots of the medium prime. But then it just works as the previous algorithm. We can also parallelize it. And the way it works is we do the smoothness testing in parallel with trial division, and then we combine all the results and we divide the value y by the products that we get from the trial division, and we test if this value is smaller than the bound for medium primes. So the latency increases slightly, but the probability to be almost smooth is much better than just being smooth. So this reduces the number of processors, but the cost that we have to pay is that now we need memory, and we need memory access for the medium prime. So the next trick that we propose is something we call pre-filtering. And the idea, we start from a simple observation that in the previous algorithm, no, I can't go, no. Okay, never mind. In the previous algorithms, in each group of processor, we try one value R to randomize, and then we spend some amount of computation in parallel to do trial division for this one particular R. And instead of doing this, we could start with several different Rs and pick one that is better than the others. Do some pre-computation in parallel on different candidates and then pick the better one. And one way we can do it is just keep one R such that the value y is small, or we can pick R such that the value y is somewhat smooth, and we do a smoothness test with a smaller bound so that we need fewer processors. And so it looks, sorry. So the parallel algorithm looks like this. In each group, we will have subgroups that pick a value R and do some tests to see if it's a good candidate or not, and then we do the rest of the algorithm. So this adds a little bit of latency, but again, we reduce the number of processors because now the probability to be smooth is better because we start from something that is better than average. And in terms of concrete numbers, we can now do it with 2 to the 40 processors. The next trick is something we call the parallel smoothness test. And here the idea is we're going to change slightly the way we do the randomization. Instead of multiplying by a value R, we're going to add R times P, where P is the size of the field we work in. So this is done, of course, as integers. If we do it as modular integers, we're not doing anything, so that's pointless. But when you do it as integer, you get different values y, and each of them has some probability to be smooth. And of course, if one of them is smooth, you can compute the root of y, and it's the same as the root of x because what you're added is 0 not p. So you can also compute the root of x from the root of y. And the nice thing when you use this type of randomization is that the smoothness test, you can now do it for all candidates y simultaneously with a single trial division. Because we know that if we take one small prime q, q will divide x plus rp if and only if r is equal to minus x times p minus 1 mod q. That's just simple modular operation. And so we just have to do one computation to compute this value, and then we know directly the candidates are that will be divisible by this particular Q. So now, if we look at how the algorithm will work, we will have a series of processors working on different small primes Q, testing for division by doing this operation here, and they will directly send results to each processor working on a given candidate R and a given candidate Y. And now we only need a single group of processor, and that's why we're going to gain in terms of complexity. And when we look at concrete parameters, we can now do it with just 2 to the 29 processors and 2 to the 40 memory, and we still have a speedup factor of around 20. So that's now a very significant speedup compared to the basic algorithm. So to summarize, we have various techniques. There are more in the paper, and we can speed up the computation of roots in FP, and this directly applies to mean root on VDO because the main operation is this root operation. And so I think the most interesting trade-off is the one I just showed, but we also have trade-offs with even fewer processors, but the speed-up gets worse. We can also apply the same techniques to Sloth++. It's a little bit more complex because Sloth++ does not use roots in FP, but in F p². So in fp², we cannot directly use smoothness because we're not really working just with integers, but it turns out that computing roots in fp², you can do it by just solving quadratic equations in the base field. And so you can apply the previous algorithm to solve the quadratic equation, and then you compute the root in fp². So this is all, in all I'm saying, the attacks are relatively theoretical because we are not really looking at concrete implementation. And in particular, one issue that will likely be problematic is the communication, because those algorithms, we're going to have something like 1 billion CPU that need to communicate and send a lot of message between each other, because we have to do this communication for each round of the VDF. So the time is actually very limited. So of course, in practice, it will be very hard to actually implement those algorithms. So it's a very clear break in the theoretical model of VDF. In practice, it's not clear. The good news is that if you look at the speed of light, it seems like it's fast enough that this could be possible in theory, but of course, in practice, it's a nightmare in terms of engineering, and it's probably not doable with current technology. To conclude, what we show in this work is that computing roots in FP is not a sequential operation. We show various trade-offs, and this clearly breaks the security claims of min root VDO and sloth++. And an interesting observation is that there are strong links with discrete logarithm. As I've explained, our algorithm look like discrete log algorithms. And so an open question is, can we use more advanced discrete log algorithms to get even better attacks on those VDFs? And that's what will be left for future work. Thank you.
Are there any questions from the audience?
Thanks, guys, for the nice talk. Thanks for the nice talk. Did you make any experiments for toy examples to see how it goes? Do you have some numbers for that?
Absolutely. We made experiments actually not even for toy examples, for full examples, but not in parallel, of course, because we don't have 2 to the 30 CPUs, but we can serialize it, and doing serially 2 to the 30 operation is completely doable. So we have implemented the full thing, and we can verify that the success rate is what we think and that it actually works. Yes, we did that.
Okay, let's thank the speaker again, and now we'll be on break.